All right, welcome back to Mr. PF's with Calculus. This is Unit 4, Day 8. And we're going to be looking at some related rate questions that deal with cones, specifically cones. For our warm-up, since I probably have some time on this one, we can go over this one. So it's very similar. Once again, we're using implicit differentiation. We are differentiating an entire equation, both sides of the equation. So they're giving us the equation. They're telling us a spherical balloon, balloon is inflated with helium at a rate of 100 feet cubed per minute. How fast is the balloon? Is radius increasing? That would be dr dt. That's the rate at which the radius is increasing at the instant that the radius is 5. So we're going to use this, since it's a sphere. So we have the formula right over here. If you differentiate the left-hand side, we get dv dt. And on the right-hand side, using our power rule, 3 times 4/3, well, actually, we can pull that out as a constant. Okay, this is the one I did here. So constant multiple. The 4/3 times pi is really just a constant, even though pi is irrational. It's still a constant. You can pull it out and then differentiate the r to the third, or you could have done 3 times 4/3, which has been 12/3, which ends up just being 4 anyway. No matter which way you do it, you're going to get the same answer, of course. And of course, remember the derivative of r cubed is 3r squared dr dt. So you have that dr dt being multiplied there. Now, we're trying to find dr dt. They gave us dv dt. So I take the 100 and I plug that in right here, which you can see. And then you solve using your algebra skills for dr dt. Second question says, how fast is the surface area increasing? So once again, they're giving you the formula here, which won't always happen. That's nice. Find the derivative of both sides using your implicit differentiation. You're doing everything with respect to time. So this is ds dt, derivative of s with respect to time. Over here, 2 times 4 is 8. 8 pi r dr dt. And then once again, you know dr dt now. So you can plug this in for dr dt. And that's how you get your final answer of 40 feet squared. Now, of course, you would need to get part A correct in order to get part B correct. All right, so let's take a look at a couple of questions here which deal with cones. The volume of a cone of a radius r. So we have ourselves a cone. Looks something like this. This is the formula for the cone. If the radius and the height both increase at a constant rate of 1/2 centimeters per second, at what rate in cubic centimeters per second is the volume of it when the height is 9? So we know the height is 9 and we know the radius is 6. All right, so once again, we know that the radius and the height are both increasing at a constant rate of 1/2 centimeters. All right, so we have our equation that they gave us. Differentiate both sides. Keep in mind that we do have product rule here involved. Now, that's going to give us a dr dt and a dh dt, but it did say that both are increasing at a constant rate of 1/2. So both this and this are both going to be 1/2. So those are the ones that they gave us. They also gave us the radius, so you plug that in here and here. They also gave us the height. So really it's just a matter of simplifying this down until you got dv dt, which is what you are looking for. That is the rate at which the volume is changing at that moment if both the radius and the height are both increasing at this rate. All right, so there's your rate. It happens to be C. All right, one more example here. This one's going to be a very common example. This is not the exact same as the last example that I gave. It says water runs into a conical, so there's my cone, tank at a rate of this. The tank stands point down and has a height of 10 feet and a base of 5 feet. How fast is the water level rising when the water is 6 feet deep? Now, here is my water level. The water level is not the entire cone, okay? So the entire cone is 10 feet high, but the water is only 6 feet high. Now, the key to this kind of question, and once again, you're supposed to know the formula for a cone. So the cone is the same formula we just had on the last example, which is right here. The issue is going to be that they're not going to give you both of the, they're not going to give you the radius and the height. So you're going to have to put one in terms of the other because you need to make it so there's only one variable. And it really doesn't matter which variable you choose, to be honest. So if you did this the way it is and r squared times height would end up needing product rule, you would have to use product rule if you're going to do this and differentiate it. you're going to end up with a dr dt and a dh dt, and you're not going to be able to do both of them. Now, so what you're going to have to do is you're going to have to get this down to one variable. So over here, I know this before we do any of this, so over here we're going to compare radius to height as a proportion. And the radius happens to be 5, and the height happens to be 10. This is the proportion of the entire cone, of radius to height. And then you cross multiply. 5 times h is 5h. Divide both sides by... Well, honestly, you could do it either way you want, but this way it's solved for r. But you really could solve for h and eliminate r. You got to eliminate one of the variables. That's the key to this question. You have both an r squared and an h. You need to eliminate one. You need to put one of the variables in terms of the other. Now that we know r really is 1/2 h, we can now replace this r with 1/2 h. So we put 1/2 h right here. It might have actually been easier to do it the other way around, because now we're going to have to square this, but it's not so bad the way it is. 1/2 squared is 1/4. Of course, you have to do h squared also. Combine these like terms, you get h to the third, and the 1/4 times 1/3 is 1/12. So we've simplified volume down to this equation with just one variable. So we don't have an r and an h. We have eliminated the r using the proportions. The proportion was that the radius is half of the height, which this makes sense. 5 is half of 10. All right, so knowing that, I know that's kind of common sense, but I wanted to show you how I arrived to that. The radius is half of the height. All right, now we can start differentiating, because now we don't have to worry about product rule. Now I've eliminated this product rule right here, because we've gotten it down to just one variable. So derivative of this is dv dt. Derivative of this part, 3 times 1/12, that's where the 3/12 came from. Of course, you got to drop this down by 1 using your simple power rule. And then you got to multiply that by dh dt. Now, dh dt, now I know I said you could do this either way, but now that I'm thinking about it, we have to have this. Okay, that's what we're trying to solve for. It says, how fast is the water level rising when... Okay, so now it makes more sense why I did it this way. So that is what we're trying to find. And if we're trying to find dh dt, then you want to eliminate radius. If we were trying to find dr dt, if that was the question, trying to find dr dt, then we would want to eliminate h. So whatever you're trying to find, you want to eliminate the other variable. So it actually does make sense to do it this way, even though the math might have been a little bit more difficult. All right, so now since we have dh dt here, we just plug in our values. The rest is really just common algebra. Plug in what h is because it tells you in the directions. Plug in what the height is. I'm sorry, what the height is and what dv dt is. And then solve for dh dt. All right, how fast is the radius of the water surface changing at that moment? How fast is the radius of the water surface changing at that moment? Well, we already know radius is 1/2 the height. Give me a second. Okay, so essentially this question is asking us to find dr dt. Now, the easiest way to do this, and I guess you could just go back to the beginning and start all over and do the same process again, but that would be a lot of work for absolutely no reason. You can literally just use the relationship that we already came up with. So we already know that the radius is 1/2 the height. If we differentiate both sides of this, because this is the proportion of one to the other, because we now know dh dt, we can actually go ahead and use this. Derivative of radius is dr dt. Differentiate this, you get 1/2 dh dt. And since we already know dh dt, which was 1/pi, we just plug that in for dh dt, and boom, there is our answer. By far the most efficient way to solve this question. I guess, like I said before, you could do this question by completely starting over from the very beginning of the original equation, but there's really no need to do that because you can use any of the formulas that you have that show the relationship between whatever. It doesn't matter if it's the volume to what the volume is or the radius to what the height is. It's going to end up working no matter which formula you use. All right, thanks again for watching and have a wonderful day, and I'll see you on the next video.